So, in late July 2026, a massive telecommunications giant took a network routing problem that usually takes them about an hour to solve, and they just crushed it in 15 seconds using a quantum system.
I mean, an hour to 15 seconds is just, it's a staggering jump.
Right. But here is the terrifying part about where quantum computing is right now. When the machine spits out an answer that fast, our current classical supercomputers are, well, they're literally too stupid to check if the answer is actually right.
Yeah, which is a wild problem to have.
It really is. So, welcome to the Quantum Briefing by TI Creative. If you're listening to this on your commute right now or, maybe prepping for a strategy meeting, you're probably thinking, I've heard this quantum hype for 10 years. Why is the day any different?
And that's a completely fair question. I mean, the skepticism is totally warranted because for the longest time, the quantum industry operated almost entirely on, promises and these futuristic timelines.
Exactly. But whether you are a tech executive trying to plan your next 5 years of IT budget, or a business leader looking for a genuine competitive edge, or, just insanely curious about the bleeding edge of physics and compute power, this deep dive is designed specifically for you.
Yeah, our goal here is to really cut through the noise.
Right. Our mission today is to separate the actual verified signal from the deafening noise. We are zeroing in on a very specific, really explosive window of time, which is the final 2 weeks of July 2026.
It was an astonishing 14 days, honestly. Like, if you were watching the industry wire, it felt like we crossed multiple massive milestones simultaneously, almost overnight.
Oh, totally.
It wasn't just, one company making some theoretical claim. It was an entire ecosystem suddenly shifting its weight.
Right, and just to set the table for you, we had IBM and the University of Chicago demonstrating what they call a massive verification of quantum advantage.
Huge.
Yeah. And then we had AT&T and D-Wave announcing the telecommunications breakthrough I mentioned at the top. Plus, Infleqtion unveiled architectural plans for a massive neutral atom system.
Right, and don't forget Quantinuum and SoftBank releasing a completely new roadmap framework for enterprise adoption.
Exactly. And on top of all that, IBM signed an agreement to acquire HRL Laboratories, which basically drags the quantum supply chain kicking and screaming into the industrial era.
And what's really fascinating here is that while those sound like 5 separate, totally isolated press releases, they are all actually pointing to one deeper industry-wide shift.
How do you mean?
Well, for years, if you wanted to market your quantum progress to the world, you basically just shouted about your raw qubit counts. You'd post a glossy picture of a golden chandelier in a lab and say, hey, look, we have 400 qubits.
Right. Look at our shiny new toy.
Exactly. Or, you published a highly controlled, incredibly theoretical benchmark record that meant absolutely nothing to a commercial enterprise.
Right, like cool for the physics department, but...
Yeah, exactly. Those metrics still matter to physicists, of course. But they are no longer sufficient for the enterprise market. The deeper story of July 2026 is that the standard of proof has completely changed.
And here's where it gets really interesting, because you can't just walk into a boardroom anymore, say the word quantum, and expect a blank check. To be taken seriously today, a quantum claim has to survive 3 distinct tests.
Right.
This is what we're calling the new standard of proof. Test number 1 is trustworthy verification. Like, can we actually trust the answer when our classical computers can't double-check the math?
Which is harder than it sounds.
Exactly. Test number 2 is integration into real workflows. Can this processor survive the messy reality of legacy code and corporate infrastructure?
Yeah, getting it out of the lab.
Right. And test number 3, deployable logical qubit systems. Meaning, is this a complete scalable system or just a science experiment held together by duct tape?
I love that framework. It's exactly what we need to accomplish today. We are going to rigorously categorize what has actually been demonstrated, what has only been, reported by companies in press releases, and what is merely planned for the future.
Got to keep those tenses precise.
Incredibly precise.
So let's jump right into that first hurdle, trustworthy verification.
Yeah.
Because we can't talk about deploying these systems into a Fortune 500 data center if we don't first fundamentally trust the math, right?
Oh.
And trusting a quantum computer is, ironically, incredibly difficult.
It really is. It's the core dilemma of the field right now.
Yeah.
And to really understand why, let's just start by defining quantum advantage.
Okay, lay it on me.
It's a phrase that gets thrown around like confetti on LinkedIn, but the definition is actually deceptively simple. It just means a quantum computer performs a useful or well-defined computation more accurately, more cheaply, or more efficiently than classical computing can accomplish alone.
Okay, that seems straightforward enough. The quantum machine beats the normal machine.
It seems that way. But the difficult phrase in that definition isn't quantum computer. The difficult phrase is then classical computing can accomplish.
Oh, because the classical machines keep getting better?
Exactly. Classical algorithms are not static. Our supercomputers are not just sitting there waiting to be beaten. There is this incredibly healthy back and forth reality in the field.
Like a rivalry.
Yeah, exactly. When a quantum research team publishes an experiment that appears to be beyond classical reach, it lights a massive fire under classical researchers. It motivates them to invent better tensor network methods or, to find some overlooked mathematical shortcut in the problem. Or they just run a much more efficient implementation on an exascale supercomputer.
So you aren't comparing a quantum processor to, like, a dusty old laptop from 2015?
No, not at all. You are comparing it to an actively evolving, highly funded, brilliantly engineered classical baseline.
Which brings us to the core dilemma, what I like to call the verification paradox. Think of it like a high school math teacher who suddenly gets an absolute prodigy in their class.
Okay, I like where this is going.
Right. So for the first few weeks, the student is just doing standard calculus.
Yeah.
The teacher knows calculus inside and out. The student hands in a test. The answer is 42. The teacher checks the work. Boom, gives them an A+ bore.
Because the classical computer, the teacher in this analogy, can easily calculate the answer itself.
Exactly. But then this genius student gets bored and starts doing, I don't know, 11-dimensional string theory topology on the back of a napkin. They hand the teacher a piece of paper with an insanely complex answer.
And the teacher has no idea if it's right.
None. It would take the teacher a million years to do the math manually to check it. So how do you grade the test? If a quantum circuit becomes too hard for the classical computer to simulate, which, by the way, is the entire point of achieving quantum advantage, how does the classical computer check the quantum computer's work?
That is the exact paradox. The very condition that makes a quantum computation valuable to a business, the fact that it can do things classical machines cannot, also makes it nearly impossible to verify.
It's a catch-22.
It really is. If you can verify it easily by just running it on a MacBook, it's not quantum advantage. If it's quantum advantage, you can't verify it.
So how on earth do we break that loop? I mean, that is where this massive July 28th paper from IBM and the University of Chicago comes in. They submitted this to RT, and I really want to dig into the mechanics of this.
We definitely should.
Because it isn't just a story about speed, right?
Yeah.
It is a story about how they tricked the genius student into showing their work.
And this paper is a landmark for exactly that reason. They had to figure out a way to give the quantum computer a test that was impossibly hard to solve classically, but somehow left, a mathematical breadcrumb trail so the classical teacher could still verify the quality of the work.
Okay, let's break down how they actually did this, because it honestly blew my mind when I was reading through the sources.
Yeah.
So to solve this grading problem, the researchers built a circuit using something called Clifford circuits.
Right.
Slow down for a second and explain what a Clifford circuit is to someone who, isn't a quantum physicist.
Absolutely. So without getting completely bogged down in linear algebra, think of Clifford circuits as a specific subset of quantum operations. They involve putting qubits into superposition and entangling them, but they do it in a very mathematically restricted way.
Okay, restrict it out.
Well, decades ago, a physicist named Daniel Gottsman and an engineer named Emmanuel Nil proved a theorem. Now it's called the Gottsman-Nil theorem, which states that a quantum computation utilizing only Clifford operations can be perfectly and efficiently simulated on a classical computer.
Oh, so Clifford circuits are the calculus in our analogy. The teacher can always grade them.
Precisely. If you only use Clifford circuits, you will never reach quantum advantage. The classical teacher can always keep up no matter how many qubits you use. The matrix math required to track them on a normal computer just doesn't explode exponentially.
But IBM didn't just use Clifford circuits, did they? They inserted something else into the mix. Non-Clifford T gates.
Yeah, and this is where the magic happens. A T-gate is a totally different kind of quantum operation. It rotates the state of the qubit in a way that introduces deep, complex quantum interference. As soon as you start adding T-gates to your circuit, the Gottsman-Nil theorem goes right out the window.
Wait, why? What physically happens in the classical simulation when a T-gate shows up?
The classical computer has to start tracking probabilities in a way that scales exponentially. With every T-gate you add, The classical memory and processing time required to simulate that circuit roughly doubles.
Just from one gate.
From one gate. So if you have a handful of T gates, your laptop can handle it. If you have 50, you need a supercomputer. If you have a few hundred, there isn't enough traditional computing power on Earth to track the math.
Wow.
Yeah, T gates are the chaotic, hyper-complex math that throws the classical computer off the rails.
So adding T gates increases the computational hardness to quantum-only levels. But here is the genius part of the IBM and UChicago experiment. They inserted hundreds of these T gates, right? Pushing the calculation far beyond classical reach.
Right.
But they did it while maintaining a structure that supported error detection. How did they pull that off?
They used a framework that relies on something called space-time codes and syndrome post-selection.
Okay, I have to stop you right there because space-time codes and syndrome post-selection sounds like something the engineer yells on Star Trek when the warp drive is failing. What is a syndrome in this context?
I know, it sounds super sci-fi, but it's a great piece of terminology once you understand it. So think of playing a game of Sudoku.
Okay, I'm with you.
You have a grid of numbers, and you know that every row must add up to a specific mathematical truth, right? In quantum computing, you have a massive problem. If you look directly at a qubit to see if it has an error, you destroy its quantum state. It's called wave function collapse.
Right, the old Schrodinger's cat problem. You open the box, the magic stops.
Exactly. So how do you check for an error if you can't look at the data? You use syndrome measurement. Instead of looking at the data qubits directly, you entangle them with helper qubits called measure qubits.
Okay, so they're like little spies.
Kind of. You aren't asking the system, hey, are you a 1 or a 0? Instead, you are asking a broader parity question, like, do the two of you have the same value or a different value?
Oh, that's brilliant.
Oh.
It's like checking if the Sudoku row is even or odd without actually looking at the specific numbers.
Yes. You extract just enough information to know if an error occurred, that signal is the syndrome, without collapsing the actual computation.
That makes total sense.
So what IBM and UChicago did was interleave those impossibly hard T-gates within a space-time code structure that allowed them to constantly run these syndrome checks.
Okay, let's look at the actual stats of this experiment, because this is where the rubber meets the road.
Yeah.
They used 97 physical qubits, but they used those 97 physical to encode 70 logical qubits.
And that distinction is absolutely critical. They didn't just fire up 97 noisy qubits and cross their fingers. They grouped them to create 70 more reliable units of computation.
Right, and they run a circuit depth of 70, meaning they performed 70 sequential layers of operations. And within that, they included 468 of those complex T-gates.
Which is way, way past the classical limit.
Right. So they are in uncharted territory. They use the syndrome post-selection to filter out the errors as they happen. Okay. And the result, they reported a 10x reduction in effective gate error rates. And they achieved and I'm reading the exact phrase here, a fidelity lower bound of 0.284 at 95% confidence. The whole run took about 15 minutes.
And just for context, IBM stated that leading classical simulation approaches would face completely prohibitive runtimes like centuries or more to do what that quantum machine did in 15 minutes.
Okay, I have to push back hard on this. I'm looking at this fidelity bound of 0.284. That translates to roughly 28%, right?
Correct.
Okay, if I am a CIO and I buy a multi-million-dollar classical server from Dell or HP, I expect it to be 99.9999% accurate. If it fails 72% of the time, I'm firing my IT director. Why on earth are we celebrating a 28% passing grade? Are we just lowering the bar so quantum looks good?
It's a fantastic question, and it highlights a major misunderstanding of what quantum fidelity actually means in this era.
Okay, enlighten me.
We are not talking about a classical server adding 2 + 2 and getting 5. We are talking about sampling from an unfathomably massive probability distribution.
Unpack that for me. What does that actually look like?
Okay. Imagine the correct answer to this algorithm is a specific sound wave playing in a massive stadium filled with screaming fans. The classical computer can't even enter the stadium.
It's stuck outside in the parking lot.
Exactly. Now, the quantum computer can enter the stadium and it records the sound. But because of quantum noise, there is a ton of static on the recording. The fidelity bound of 0.284 is a statistical certificate.
Meaning what?
It proves mathematically that the core signal, the correct sound wave, is definitively present in the recording, and it retains at least a 28.4% overlap with the perfect ideal state.
Wait, so it's not saying 28% of the time it's right and 72% of the time it's entirely wrong? It's saying the correct signal makes up 28% of the total messy output.
Exactly. And in quantum sampling, once you have a mathematically proven signal that's strong, you can amplify it and extract the correct answer. It is proof of verifiable quality in a regime where verification was thought to be nearly impossible.
Wow. All right, I'm tracking with you now. But still, if IBM calls this quantum advantage, is the debate over? Like, have we crossed the finish
I
line?
have to be rigorous here. No, the debate is not over. There are massive caveats to this.
I figured as much.
First, it is a device-dependent certificate, meaning it relied heavily on the specific error profile of IBM's hardware. Second, this is a new paper submitted to ArcSFIF in late July. It has not yet survived the brutal gauntlet of independent, double-blind peer review.
Which takes months, if not years.
Exactly. But to IBM's credit, they aren't hiding from this. They took this 15-minute result and put it on their public quantum advantage tracker.
That is such an aggressive move, a public tracker. It's basically an open challenge.
It is absolutely throwing down the gauntlet. It is an open invitation for every brilliant classical algorithm designer on Earth to look at this and say, hold my coffee, I bet I can write a classical tensor network algorithm that can beat your 15-minute time.
So they want people to try and tear it down.
They do. They are inviting the world to challenge the hardness boundary, to question the mathematical assumptions, and to debate the cost comparison.
But if I'm a business leader, I might hear the word debate and think, okay, the science isn't settled. Call me when it's done. But that's the wrong way to look at this, isn't it?
Completely wrong. That debate is not a weakness in the technology. It is the scientific process functioning at its highest possible level. Advantage is not a marketing label that magically ends the conversation forever.
Right.
It is a claim that begins a much more demanding, much more rigorous conversation. The fact that the bar is this high means the technology is genuinely maturing.
A claim that begins a more demanding conversation. That is the perfect segue. Because let's say IBM is 100% right. Let's say we completely trust the math. We have this verified fidelity. The genius student has proven they aren't cheating.
Right.
That is only step one.
It really is.
Step two, which is the second test in our new standard of proof, is getting that computation out of the pristine, temperature-controlled laboratory and into the real world.
The messy real world.
Exactly.
Yeah.
If I take that genius student who is great at math in a quiet room and I drop them into the middle of a chaotic, screaming AT&T dispatch center, do they panic? Because integration into real corporate workflows is where so many promising technologies go to die.
I mean, that's probably the hardest test of all, right? It's the difference between theoretical physics and applied enterprise engineering.
And this brings us to the July 27th announcement from AT&T and D-Wave. We talked about this at the very beginning of the deep dive. The reported benchmark here is staggering.
It really is.
AT&T took an early network optimization workload that traditionally required roughly 1 hour to solve using their classical systems. Using D-Wave's technology, they got that time down to less than 15 seconds.
1 hour to 15 seconds. I mean, when a supply chain manager or an operations director sees a metric like that, their heart literally skips a beat.
Right. And off the back of that pilot, they announced an expansion of the agreement. They're going to explore outage detection, technician routing, network build planning, and traffic management.
It's a huge expansion.
Let's step back and look at the business logic here. Why telecommunications? Why is a telecom giant the one seeing this kind of traction, as opposed to, say, a retail bank?
Well, if we break down the problem class, telecommunications is the perfect storm for quantum optimization. Telecom networks are not static entities. They are massive, living, breathing puzzles that change every millisecond.
Give me a real-world example of that.
Think about the operational reality of AT&T. On any given Tuesday, they have to allocate bandwidth dynamically across millions of cell phones. They have to route thousands of technicians in real time. They have to plan fiber optic builds that cost tens of millions of dollars.
And then something goes wrong. Like a backhoe accidentally cuts a major fiber trunk in downtown Seattle.
All right. And suddenly the network has to instantly reroute traffic to avoid a massive SLA violation while simultaneously dispatching a repair crew.
Under a crazy amount of constraints.
Endless constraints, union rules for driver hours, truck inventory, physical distance, traffic patterns, power costs. It's overwhelming.
It's the classic traveling salesman problem, but on steroids, with 1,000 moving variables.
Exactly. Mathematically, it is a combinatorial optimization problem. As you add variables, more trucks, more broken lines, the number of possible solutions explodes factorially.
Just like the T-gates we talked about earlier.
Yes. Very quickly, you have more possible routing combinations than there are atoms in the observable universe. Classical computers get bogged down trying to sift through all those possibilities.
And this is exactly what D-Wave is built to solve. But I want to pause here because we really need to clarify something. Earlier, we were talking about IBM and gate-based quantum computers using T-gates and Clifford circuits.
Right.
D-Wave doesn't use those, do they? They use something called quantum annealing. What is the actual difference?
It is a fundamentally different approach to utilizing quantum mechanics. A gate-based machine, like IBM's, is like a highly complex, programmable calculator.
Okay.
You feed it a sequence of logical operations, do this, then flip this, and it runs an algorithm. A quantum annealer is not a universal calculator. It is a highly specialized physical system designed to do basically one thing: find the lowest energy state of a complex landscape.
Give me a visual for that.
Okay, imagine a massive physical landscape made of hills and valleys. You are blindfolded, and your goal is to find the absolute lowest point in the deepest valley.
Okay, I have my blindfold on.
In our telecom example, that deepest valley represents the absolute fastest, cheapest route for the technicians.
So how does a classical computer solve it? If I'm blindfolded, I'm just feeling the ground.
Yeah, exactly. A classical algorithm basically has to walk. It starts at a random point, fields the slope of the ground, and walks downhill. When it hits the bottom of a valley, it says, "I found it."
But wait, what if it's just a small valley?
That is the exact problem. It might just be a shallow valley, the mathematicians call a local minimum. To find out if there is a deeper valley over the next hill, the classical computer has to climb up the hill and check.
Which takes time. And if there are a billion valleys, it takes an hour to check them all.
Exactly. Now, here is how a quantum annealer does it. It uses a quantum mechanical property called quantum tunneling.
Oh, that sounds cool.
It's amazing. Instead of walking over the hill, the quantum system literally tunnels through the mathematical hills. You map your business problem onto the physical qubits. You start them in a simple, known energy landscape. Then you slowly, adiabatically change the magnetic fields until the landscape represents your AT&T routing problem.
And then what?
If you do it carefully enough, the qubits naturally settle into the absolute lowest valley without having to climb over every single hill.
It just phases through the terrain and pools at the bottom.
Yes. It leverages physics to find the minimum energy state, which correlates directly to your optimal business solution. It is incredibly fast for highly specific optimization problems.
That is a brilliant explanation. And that specialization leads directly to the architectural breakthrough AT&T is utilizing here. Because one of the biggest fears enterprise CIOs have is that quantum is going to force them to completely rip and replace their entire IT stack.
Which nobody wants to do.
Nobody. But AT&T isn't doing that. I call this the quantum sous chef architecture.
The sous chef, I like that.
Yeah. Imagine you run a massive Michelin star restaurant. The kitchen is chaotic but functional. One day, you buy a hyper-advanced $50,000 laser-guided blender.
Okay.
You don't fire your entire kitchen staff.
Yeah.
You don't ask the blender to take reservations or cook the steaks or wash the dishes. You keep your head chef, the classical system, in charge.
Right, because the classical system is already good at all that.
Exactly. The head chef delegates the incredibly complex pureeing of a specific sauce to the laser blender while the rest of the kitchen keeps humming along.
That is a very, very accurate representation of modern hybrid architecture. AT&T is not building a standalone quantum dashboard that sits in a corner and requires a PhD physicist to operate. No enterprise wants another dashboard.
Definitely not.
What they're doing is layering D-Wave solver into their existing classical agentic AI systems. The architecture is beautifully practical. The classical AI agent is your head chef.
Right.
It monitors the network. It receives the alarm that a fiber was cut in Dallas. It pulls the historical data, the corporate policies, the technician locations, and it runs the user interface.
All the messy enterprise stuff that classical computers are already great at.
Exactly. And then for that one specific mathematically punishing step, finding the fastest route out of a trillion combinations, the classical agent reformats the problem and pings the quantum annealer via an API call.
So simple.
The annealer acts as a highly specialized sous chef, crunches the optimization in seconds, hands the answer back, and the classical system executes the dispatch.
And there's a hidden massive benefit to this architecture, which is resilience. What happens if the quantum service goes offline? Or if the routing problem is just, 3 trucks in a small town and doesn't even require a quantum computer?
The system seamlessly falls back to a classical solver. The workflow does not break. The customer never knows the difference. Quantum becomes a powerful, callable component, not a single point of failure for the entire stack.
Okay, that all sounds amazing. But it's my job to be the skeptic here.
Please do.
I saw the LinkedIn hype train the day this was announced. People were calculating the percentage decrease from 60 minutes to 15 seconds and literally posting, "Quantum computing will make your business 14,000% faster today. Book a consultation with me."
Oh, I saw those posts too.
Right. So can we just assume everything is thousands of times faster now?
We absolutely cannot. This is where we have to ground the discussion in rigorous, borderline cynical skepticism. We have to separate the verified from the reported.
Okay.
This AT&T result is a company-reported benchmark. It is a press release. It is not an independently peer-reviewed academic paper.
So you're saying they might be juicing the numbers?
I'm saying they are telling the story that makes the partnership look as successful as possible, which is what companies do. But as analysts, we have to note that the announcement is missing vital contextual data.
Like what?
Well, first, we don't know the exact mathematical definition of the workload. Was it a full national routing problem or a highly simplified toy model?
Right. That makes a big difference.
Second, what was the classical baseline? When they say it used to take an hour, was that hours spent running a state-of-the-art heuristic solver on an AWS supercluster, or was it a legacy piece of software written in 2008 running on a server in a basement?
We don't know.
We have no idea. And what about the end-to-end latency? If it takes 59 minutes to extract the data, clean it, and format it so the quantum computer can understand it, and then the quantum computer solves it in 15 seconds.
Your end-to-end workflow time is still an hour.
Precisely. You have to account for pre-processing, latency, and access costs. You cannot blindly generalize a claim of 1 hour to 15 seconds to every problem in your supply chain.
So if the speed-up metric itself is a bit fuzzy, what is the actual takeaway here?
The true value of this announcement isn't the 15 seconds. The true value is the operational commitment.
The fact that they're expanding it?
Yes. AT&T saw enough genuine value in that initial test to expand the relationship into their real enterprise architecture across multiple distinct use cases. They are putting money and engineering hours behind the integration layer. It proves the technology is moving from the physics lab to the IT department.
Which is a massive leap. And that transition from lab to data center brings us perfectly to our third test in the new standard of proof. Deployable logical systems.
Yes.
Because we have verified math and we have hybrid integration patterns. But what will the actual physical hardware look like when it rolls onto a data center floor?
That's the big question.
And to understand that, we have to completely banish a specific phrase from our vocabulary: raw physical qubits.
I mean, this is perhaps the biggest and most necessary conceptual shift for the industry right now. If you are still counting raw physical qubits, you are living in the past.
And to explore this, let's look at the July 22nd announcement from a company called Infleqtion. They unveiled plans to deliver a fault-tolerant, neutral atom quantum computer to the Illinois Quantum and Microelectronics Park in 2027. And the target numbers they announced are critical to this conversation. The system is designed to demonstrate more than 50 logical qubits on a path to 100, utilizing an architecture of over 1,000 physical atoms.
Those numbers, 50 logical, derive from 1,000 physical. They are the Rosetta Stone for understanding the entire future of quantum hardware.
Okay, let's break this down into plain English.
Yeah.
We hear these terms constantly, but what is the actual physical difference between a physical qubit and a logical qubit? Let's start with the physical.
Okay, a physical qubit is the actual tangible thing in the real world that is storing the quantum information. Depending on the company building the machine, that physical thing could be a superconducting circuit cooled to near absolute zero, it could be a photon of light traveling through a fiber, or it could be a single ion.
In Infleqtion's case, they use neutral atoms. Yeah. How does that physically work? Are they just like floating in a box?
It's basically sci-fi technology made real. They use arrays of lasers to trap individual uncharged atoms in a vacuum chamber. The lasers act like optical tweezers, holding the atoms suspended in a perfect grid.
That is wild.
Right. They then use other lasers to manipulate the electron states of those atoms to perform computations.
But here is the problem with physical qubits. Regardless of whether they are trapped atoms or superconducting loops, they are incredibly, agonizingly fragile.
Beyond fragile. They exist in a delicate quantum state of superposition. Any environmental noise, and I mean any noise, can destroy the calculation.
Like what kind of noise?
A tiny fluctuation in temperature, a stray electromagnetic field, even a cosmic ray hitting the processor from space can cause a physical qubit to flip its state from a 1 to a 0 or change its phase.
They are the most sensitive divas in the universe. If you look at them wrong, they forget their lines and ruin the play.
That is a very accurate way to put it. So if you try to run a deep, complex calculation on just physical qubits, the errors accumulate exponentially. Before the calculation even finishes, the answer has turned into pure statistical garbage.
And that is where logical qubits come in.
Exactly.
So a logical qubit isn't a physical thing.
Correct. A logical qubit is a conceptual encoded unit of computational power. It is protected by distributing its information across a large grouping of physical qubits using highly advanced error correction algorithms, like the surface codes we talked about.
Earlier, we used a team effort analogy, but I was thinking about this, and it's more like a choir.
Oh, a choir is a fantastic analogy. Walk me through it.
Okay, so if you have one single singer, a physical qubit, performing a solo, and they suddenly forget the lyrics or they cough, the song is ruined. The calculation fails.
Right.
But if you have a choir of 100 singers all singing the exact same note together, they represent one single musical output, the logical qubit.
I see where you're going.
If one singer in the back row forgets the lyrics or coughs, the audience doesn't even notice. The other 99 singers cover for them. The song survives. The director can hear the one mistake, correct the singer, and keep the song going.
That is a beautiful way to describe quantum error correction. The system uses a whole cluster of physical qubits to represent just one piece of reliable quantum information.
Because of the entanglement.
Because they are entangled and governed by syndrome measurements, like we discussed with the Sudoku analogy earlier. If one physical atom gets hit by a cosmic ray and flips, the system detects the anomaly and corrects it dynamically without losing the underlying logical information.
Ah, so that is why Infleqtion needs an architecture of over 1,000 physical atoms just to create 50 logical qubits.
Yes.
There is a massive overhead required for the error correction. You need a lot of singers in the choir to protect the one note.
You do. And the exact overhead ratio depends on the hardware modality and the specific error correction code being used. Some might need 10 physical qubits per logical, some might need 1,000.
But the principle is the same.
The fundamental reality is universal across the entire industry. One reliable logical qubit represents exponentially more computational power than dozens or hundreds of unprotected physical qubits.
And this is why the entire industry vocabulary is shifting. If a vendor comes to you tomorrow and says, hey, we just built a 500-qubit machine, your first question should no longer be, wow, when can I use it?
Definitely not.
Your first question has to be, are those physical or logical? Because 500 physical qubits without error correction might be completely useless for a deep enterprise simulation, whereas 50 logical qubits could cure a disease.
That is the exact shift in mindset we need. We are moving away from raw counts and toward metrics that actually dictate performance, like logical qubit count, logical circuit depth, and gate fidelity.
And looking closer at Infleqtion's plan, what caught my eye isn't just the qubit count, it's the systems level thinking.
Yeah, they really thought it through.
They highlighted integration with NVIDIA's Infleqtion, which is a fabric that connects the quantum processor directly with classical GPUs. And they are targeting very specific energy grid applications for this Illinois facility, things like unit commitment, contingency analysis, and nuclear fuel loading.
And that combination is what makes the announcement compelling from a commercial perspective. They aren't just selling a generic physics box. It's a planned system, featuring a high-speed hybrid compute interface with GPUs, an access model through a national testing center, and a highly specific industrial application domain. This is how infrastructure buyers actually think.
They don't buy qubits, they buy systems that solve grid optimization problems.
Exactly.
But I know you're going to pull us back to reality here. We have to enforce the new standard of proof.
Right.
We are looking at the planned versus demonstrated distinction. Is this real today, or is it vaporware?
We absolutely must emphasize the precision of the tense used in their announcement. This is a future plan aimed at 2027. The system is, quote, designed to demonstrate this capability.
So it hasn't done it yet.
It has not yet delivered 50 logical qubits.
So it's an incredibly detailed architectural blueprint, but it's not a finished house I can walk into today.
Correct. It is a vital, incredibly important signal of where the hardware and the deployment infrastructure are heading. It shows that vendors are preparing for enterprise-scale integration. But on our ledger of truth, it belongs firmly in the planned column.
Which raises a really difficult question for the audience. If these deployable logical systems are still largely in the planning phase, and the timelines are 2027 or beyond, how do business and technology leaders plan their investments today without chasing ghosts?
It's a tough spot to be in.
If I'm a CIO, how do I build a roadmap when the hardware itself is still a moving target?
Well, this is where we have to fundamentally abandon the old way of thinking about technology adoption. For years, executives have asked one very specific, very flawed question.
Which is,
When will quantum computing be useful?
right, just give me the date. Is it 2028? Is it 2032? Just tell me when to write the check so I can put it on my calendar.
Exactly. And the July 21st white paper, released by Quantinuum and SoftBank, brilliantly deconstructs why that is the wrong question entirely.
How so?
That question assumes there is one single magical universal date when the entire industry crosses a finish line from useless to useful.
Like the flip of a switch. On Tuesday, it's a science experiment. On Wednesday, it runs the global economy.
Exactly. But no such date exists. Instead, Quantinuum and SoftBank introduced a framework that maps specific business use cases to specific stages of hardware maturity.
So it's a sliding scale. Explain how this portfolio approach works in practice.
It means you stop asking, when is it useful? And you start asking, which specific problem class in my business becomes executable at which stage of hardware maturity?
It turns a generic technology forecast into a strategic, risk-adjusted portfolio.
Precisely. Let's use some examples from their paper to make this concrete. They contrast two totally different fields, quantum chemistry and graph analytics.
Okay, let's say I'm a massive pharmaceutical company, and I want to simulate a complex new protein molecule to cure a disease. That requires absolute ground-state chemical accuracy. I can't have a 28% fidelity there. I need perfection.
Exactly. To simulate a complex molecule perfectly, you might need thousands of flawless logical qubits and massive circuit depths capable of millions of sequential operations. That specific problem might legitimately be 10 or 15 years away from execution.
Okay, but what if I am a logistics company looking at a supply chain scheduling problem? I just want to optimize the flow of shipping containers. I don't need molecular perfection. I just need a 5% improvement over my classical baseline to save $50 million a year in fuel.
And that is a completely different threshold. You might not need perfect logical qubits for that. You might be able to extract that 5% value using a hybrid, noisy quantum annealer or a shallow gate-based circuit much, much earlier.
Maybe even today, as we saw with the AT&T dispatch example.
Exactly.
This makes so much sense. You treat quantum adoption like an investment portfolio.
Yes.
For your advanced chemistry division, the rational decision is we will monitor the science and wait for 500 reliable logical qubits in 2030. For your logistics division, the rational decision is we are going to pilot a hybrid solver right now in 2026.
Right.
And for your finance division, doing risk analysis, the decision might be we will run a rigorous benchmark test once a year to see if the hardware is caught up to our models. All three of those are the correct answer simultaneously.
Precisely. You document the business value, the data requirements, the classical baselines, and the validation criteria for every single problem in your inventory. And then you wait for the hardware to hit the specific threshold for that specific problem.
But the hardware hitting those thresholds requires an absolute manufacturing miracle. And that brings us to the final major headline of that crazy 2-week period in July.
The industrial stack.
We have to talk about the widening industrial stack because building these machines is getting incredibly complex. On July 23rd, IBM announced an agreement to acquire HRL Laboratories.
This was a massive, massive signal regarding the physical supply chain of quantum computing.
For a little context for the audience, HRL Laboratories was owned jointly by Boeing and General Motors. It's an advanced research facility with deep roots in aerospace and automotive tech, and IBM is bringing them in-house.
Right.
Why? Because HRL brings world-class expertise in silicon spin qubits, quantum sensing, cryogenics, control electronics, advanced packaging, and material science.
It is a breathtaking list of physical engineering capabilities.
But I'm going to play devil's advocate here again. If I'm a software CIO at a bank or a supply chain executive at a retailer, why on earth do I care about cryogenics and packaging? I don't care how cold my current Dell servers get, as long as they don't catch fire. Why does an acquisition of a physics lab matter to my business roadmap?
You should care because it signals a fundamental, irreversible shift in the market. It proves that the quantum race is no longer just a physics experiment about isolating a single qubit in a university lab.
What is it now?
It has become a ruthless industrial systems race.
An industrial systems race.
Think about the physics of scaling. To go from Infleqtion's 50 logical qubits to the 5,000 logical qubits required to solve that pharmaceutical chemistry problem, vendors cannot rely on bespoke, handcrafted, duct-taped laboratory setups.
Right, you can't hand solder 10,000 microscopic wires.
Exactly. They need immense manufacturing consistency. They need advanced packaging to route thousands of microscopic control wires into a vacuum without generating a single fraction of a degree of heat.
That sounds impossible.
It's incredibly hard. They need massive cryogenic refrigerators, specifically dilution refrigerators. We are talking about cooling these chips to millikelvin temperatures. That is colder than the vacuum of deep space.
Wow.
And they have to do it reliably, 24 hours a day, 7 days a week, in a commercial data center, without the helium-3 leaking.
So IBM acquiring HRL is essentially them saying, the physics works, now we have to secure our supply chain for the next decade of industrial commercial scaling.
Exactly. They are vertically assembling the capabilities across the entire physical stack: fabrication, packaging, microwave controls, cooling, orchestration, error correction, and finally, software.
Now, the caveat here, because we always enforce the new standard of proof, is that this acquisition is subject to regulatory approval, the financial terms were not disclosed, and acquiring a world-class lab does not magically upgrade IBM's deployed data center systems overnight.
Right, it's a long-term play.
It's a long-term infrastructure play. But it proves beyond a shadow of a doubt that the era of the lab experiment is ending and the era of industrial manufacturing has begun.
Absolutely.
Which brings us finally to the so what. We have separated the reality from the hype. We've talked about verification and the math paradox. We've talked about AT&T and hybrid integration. We've talked about physical versus logical systems and the industrial supply chain.
We've covered a lot of ground.
Let's land the plane. Based on these three tests, what exactly should the listener be doing in their organization on Monday morning?
This is the most important part of the conversation, because the organizations that prepare now are the ones who will survive the transition.
So if I'm a CIO listening to this, what's my homework? You mentioned baselines earlier. I assume that's step one.
Let's actually start one step before that.
Okay.
Building a problem inventory. Do not just look around your company and say, where can we use quantum? That is a solution looking for a problem, and it will fail.
Guaranteed to fail.
You need to sit down with your department heads and identify specific operational decisions where latency, simulation cost, or solution quality has a highly quantifiable business value.
Show me the money.
Exactly. If you cannot attach a hard dollar amount to the optimization, there is no ROI for quantum. If finding a 10% faster trucking route saves you $20 million a year in fuel, put it on the list.
But if simulating a new material saves you $200 a year, ignore it.
Right. Build a ruthless, ROI-driven inventory of problems.
And once you have that list, that's when you establish the baselines you mentioned.
Yes. Establish serious classical baselines. For every problem on that inventory, you must rigorously record your absolute best classical solver, not your average solver, your best.
Right.
Record your current hardware, your runtime, your operating costs, and the staffing required to run it.
And this is where companies actively trick themselves, right?
Constantly. It drives me crazy. I have seen massive organizations put a team of brilliant PhDs on a quantum pilot project for 6 months. And when they present the results, they compare the quantum system against a classical algorithm that was written by an intern 3 years ago, running on a standard desktop computer.
Of course, the quantum system looks better. It's a rigged fight.
It's an illusion that wastes millions of dollars. A quantum pilot must compete with the most aggressive, heavily optimized, heavily funded, state-of-the-art classical alternative your company can possibly deploy.
Do not intentionally weaken your classical baseline just to make the shiny new quantum toy look good to the board.
Exactly.
That is fantastic practical advice. What about the news cycle? Because we just spent an hour decoding 5 announcements. How should a business leader process the fire hose of quantum news?
You have to mandate organizational discipline. I call it labeling your evidence. When a vendor pitches you or a news article drops, you and your team need to instantly, mentally categorize the information.
How so?
Is this a peer-reviewed academic result? Is it a new preprint like the IBM and UChicago paper that still needs verification? Is it a vendor-reported commercial benchmark like AT&T and D-Wave, which lacks independent validation? Or is it a future architectural plan like Infleqtion?
By putting these into distinctly different mental columns, you instantly strip away 90% of the confusion and hype. You stop reacting to 2027 future plans as if they are present realities you need to deploy tomorrow.
Precisely. Next, when you actually start building, you must design hybrid workflows. Remember your quantum sous chef analogy.
Keep the classical chef in charge.
Always. Assume that your data preparation, your API orchestration, your user interfaces, your security policies, and your monitoring will remain entirely classical.
Do not try to rewrite your entire ERP system in quantum code.
Treat quantum as a highly specialized, callable resource with robust classical fallbacks. If you design your architecture this way today, you preserve your value even as the underlying quantum hardware completely changes over the next 5 years.
Right. If a new vendor invents a better qubit in 2028, you just swap out the solver on the back end via an API, and the rest of your enterprise workflow doesn't even blink.
Exactly. And while you are running these workflows, track the right metrics. Stop asking how many physical qubits a machine has.
We established that's a vanity metric.
It is a vanity metric. If a vendor pitches you on physical qubits, push back. Start tracking logical qubits, logical operations, circuit depth, gate fidelity, total time to solution, and the actual financial cost per run. Those are the metrics that dictate true enterprise utility.
And finally, how do we know when to pull the trigger on full deployment?
Set reevaluation triggers. As we learned from the Quantinuum and SoftBank framework, do not predict a magical date. Define specific mathematical thresholds.
Give me an example.
Tell your engineering team, when a vendor can demonstrate 40 logical qubits with a 99.9% logical fidelity rate on our specific supply chain dataset, that is the exact day we release the budget for a full commercial integration.
It takes all the emotion out of it, takes the hype out of it. It's just math and business logic.
Exactly.
So to summarize this incredibly deep dive, the final 2 weeks of July 2026 did not prove that quantum computing is perfectly ready to solve every single problem in every business today.
No, it didn't.
But what it did was aggressively raise the standard of the conversation. IBM and UChicago proved we have to focus on the paradox of verification. AT&T and D-Wave showed us the necessity of resilient, hybrid integration. Infleqtion showed us the critical leap from fragile physical atoms to stable logical qubits.
Right.
Quantinuum showed us how to build a rational portfolio roadmap. And IBM buying HRL showed us the brutal reality of the industrial supply chain.
The standard of proof is higher now. You can't just wave your hands and say quantum. And frankly, for the leaders listening, asking better, harder questions is your true competitive advantage right now.
The organizations that master these 3 tests, verification, integration, and deployable systems, are the ones who actually capture the value when the hardware matures.
Absolutely.
And I want to leave you, the listener, with one final, slightly provocative thought to mull over.
Oh, let's hear it.
We spend all this time talking about when the quantum hardware will finally be ready. We obsess over the cooling and the lasers and the qubits. But what if the most immediate, tangible return on investment for quantum computing isn't the quantum hardware itself?
What is it then?
What if the real value is that preparing for quantum forces your organization to finally audit, clean up, and rigorously optimize its deeply flawed classical workflows?
I see this happen so often. In doing the prep work and establishing those serious classical baselines and cleaning up the data pipelines for the quantum pilot companies, discover massive, glaring inefficiencies in their classical systems that they can fix today.
Exactly. You might find tens of millions of dollars in business value just in the preparation phase, long before a quantum processor ever boots up in your data center. Because if you want to verify the genius student's math, you first have to make sure your own math is perfect.
It forces an operational discipline that most organizations desperately need.
It really does. Because when you're dealing with the diagnostic muddy waters of the quantum frontier, the only way forward is absolute rigorous clarity. Thank you so much for joining us for this deep dive. You are officially the most well-informed person in your next strategy meeting. This has been the Quantum Briefing by TAI Creative. Keep asking the hard questions, and we'll see you next time.